Great, thanks. Yeah, and welcome everyone. So my goal is to tell you about how we can understand a little bit about what we understand about the telescopic category through the lens of K-theory. And uh, I'm really going to focus a lot on the point of view that TC is a tool that we can use to try to understand the telescopic category. So there are really a lot of aspects to the story, and I really want to focus on um, things related to TC. And so today I just want to tell you, um, give you sort of an overview. So I want to explain the telescope conjecture, and I want to sort of sketch the reduction of the disproof of the telescope conjecture to statements about TC. And yeah, so I'm really not going to give the full background on the telescope conjecture. And really, if you wanted to learn more, one thing you can look at is see Doug Ravenel's uh, mini course, which he gave an ECHT about the background and history of the telescope conjecture. So I'm going to sort of give less of that. Okay, so let me get started, unless there are any questions. So to maybe explain, maybe I'm going to first try to explain a little bit about telescopes. And so what are telescopes? Well, I want to say that telescopes, they naturally arise from the study of the sphere spectrum, uh, uh, similarly to how the sort of prime fields like Q and Fp arise from the study of the integers. So maybe I'll explain what I mean by that. So if you're interested in something about the integers, like some question about the integers, one natural way to do this is you first understand that question rationally. So you take the integers and you invert all the primes. And that doesn't capture everything about your original problem, but you sort of can understand often the sense in which it doesn't capture everything, and the sort of piece of information that's missing comes from understanding the integers modulo some power of a prime. And so in this way, you can decompose a lot of arithmetic questions into questions about the integers and sort of p-adic questions. And maybe I will point out that the reason that these are the natural objects to break it up into and you can't do anything more is because these are sort of indecomposable in the following sense. So if you look at z mod p to the n, every element is either a unit or nilpotent in the sense that some power of it is zero. And so the kind of things that you'd want to invert they have to be things that are not nilpotent, because if you inverted a nilpotent element, you get zero. And so in some sense, this is sort of the maximal decomposition of the integers. And you can sort of can recover the integers or even its module category from this decomposition. For example, you can write the integers as the pullback of the profinite integers, which is just the product over p-adic integers of all primes, and the rationalization of that. and the rational numbers. So this way you can sort of reconstruct the integers from this data. And so you could try to run a similar story about the sphere spectrum. So starting with the sphere, you can do exactly the same thing. So you can invert all the primes. And when we do that, we know exactly what happens. We again just get the rational numbers viewed as a spectrum. And again, the piece of information that was missing was exactly the p-adic information. So the sphere is mod p to the k as k varies. And the point of telescopes is that you're not quite done when you're working with the sphere, and the reason is the following: it's because of a theorem of Devenant, Hopkins, and Smith. Well, in this case, it's really due to atoms, but maybe here's the more precise statement due to Devenant, Hopkins, and Smith. So the nilpotence and periodicity theorems of Devenant, Hopkins, and Smith, they show that if you look at pi star of S mod p to the k 0, that this is actually isomorphic. If you look at this modulo nilpotence, then this is just a non-trivial subring of just a polynomial ring on a single class V1, where V1 has degree 2p minus 2. And so what this is saying is that if you think about all the ways you could break this up further, which would involve inverting and modding out by some additional element, you essentially only have one choice, which is this element V1 or some power of V1. And so what you can do then is you can continue to break it up into more pieces. So you can start with sphere mod p to the k naught, and you can invert V1. And then you can also take the sphere mod p to the k, and you could take the cofiber of multiplication by some power of V1, which I'll write as this. I'll just denote that like this. And the great thing is that, in fact, we know how to completely compute the homotopy groups of these things, for example. And so the hope is that you can sort of continue this process and break understanding the sphere spectrum into these pieces that you could try to understand. So let's first see why we can keep doing that. Well, the reason is because I didn't tell you, well, it's because the theorem of Devenant, Hopkins, and Smith goes further than that. It tells you that you can sort of keep going. So you can inductively construct objects that look like you've quotiented out by a sequence of elements. And they show that the homotopy groups of that modulo nilpotence are just a non-trivial subring of this polynomial ring, where the degree is 2p to the n minus 2 of some class called Vn. And so what this tells you is that you can sort of keep going. So you can take the sphere, mod p v1 to the k1, and then invert v2. And then you could also have modded out by v2. And the reason, okay, I wrote inverting v2 or v1, but it's really inverting some power of it. But the point is that it didn't really matter. It doesn't depend on which power you chose because of this fact. So it's sort of okay notation to write this. So you can keep going. Okay. So what that tells you is that you can decompose the sphere and really the homotopy groups of the sphere into pieces that are built from what's called a telescope, which is this kind of object. So you mod out by some of these VI operators, and then you invert the next one. And so this is a telescope of height n, and this object is what I'll call a type n generalized Moore spectrum. And I'll denote this capital Vn. And I'll denote this telescope by Vn adjoint Vn inverse. Okay. So okay, so right. So this approach tells you that maybe to understand the homotopy groups of spheres, you could try to understand these telescopes first. And there's sort of there's a nice categorical way to set this up that makes it clear that this is a reasonably natural way to do things, which is you can consider the full subcategory of spectra called Tn local spectra, which is what it is it's the subcategory generated under limits by some telescope tensored with an arbitrary spectrum. So you can look at the subcategory, and the inclusion of the subcategory has a left adjoint, which I'll give two names to, either Tn localization or subscript Tn. And so, for example, if you apply this LTN to to this Vn, this generalized Moore spectrum, then you exactly get the Moore spectrum after inverting Vn. Okay. And more generally, if you apply it to some general spectrum, there's just a pretty concrete formula for it. Namely, it's the limit over k naught all the way up to, as these numbers vary, of x tensored with the sphere mod p to the k0, v1 to the k1, all the way up to vn minus 1, to the kn minus 1, and then you invert vn of this. If you take the inverse limit over that, you get this. And this is sort of just a very canonical. So this is saying that this is really just a very canonical operation. For example, this is a symmetric monoidal category, and this is a symmetric monoidal presentable stable localization. Okay, so there's this very canonical thing you can do, which tries to capture this information that these telescopes capture. And so maybe the key question is, how do you compute the homotopy groups of these telescopes, or anything in this telescopic category? And so here's sort of here's sort of some approach to trying to do that. What you could do is try to use the Adams-Novikov spectral sequence. So in other words, you can compare your Tn localization of x to the following limit over the simplex category, of you can take tensor powers of the complex Bordism spectrum, and you can tensor that with X, and then you can T and localize that. So this is usually if you want to if X is like a finite spectrum and you want to compute the homotopy groups of X, writing this formula without the T localization would do that, describe it in terms of its MU homology. And so you might hope that this does the same thing. So this formula is called the KN localization of X. And I mean, it's also a very canonical thing. So for example, you can write over here, there's actually another symmetric localization, which is KN localization. Or I'll also write it as subscript KN. And so, yeah, and so the point is that this is actually something that you can often compute. So pi star is computable in terms of algebra, maybe plus a bit more. Okay, and so you'd hope that this is in fact just telling you everything about your telescope. And so Ravenel's telescope conjecture it asks, is this map, let's call it C, is C an isomorphism for all X? Or equivalently, there's sort of some equivalent ways to formulate it. So you can also formulate it as saying, is the KN local category the same thing as the TN local category? Or another way to say it is essentially because these categories are generated by specific telescopes, you can just ask, is Vn adjoint Vn inverse equal to the KN localization of Vn? Okay. And so for n equals 1, this is true. And this is the result of Miller and Mahold. And this is really the reason why I said over here we actually know pi star. It's because of the fact that the telescope conjecture is true. And so the goal of this mini course is to explain some ideas behind why it's false for n at least 2. That's one of the goals. Okay, so one way to think about the telescope conjecture is it's sort of saying that MU, you can use MU completely to completely understand these telescopes. And so if you want to show, if that's not the case, then you need something that's sort of better capable of understanding telescopes. And the point here is that K-theory and topological cyclic homology are going to be tools that you can use to better understand information about telescopes than MU can. So you need something better than MU to detect pi star of telescopes. And the idea is that you can use certain algebraic K-theory spectra. So it's not going to be super important that you know a lot about algebraic K-theory for the purposes of this mini course, I'm really, you can view it kind of as a black box, and I'm not going to discuss it really for the rest of the lectures. It will mostly just be today. So K-theory, it's some functor that takes an algebra in spectra to a spectrum called the K-theory of R, and it sort of, it encodes, maybe to give you a feeling for what it is, it encodes some sort of stable information about the category of modules of R. So it's some sort of categorical. It's really not invariant of R, but it's invariant of its category of modules. And so the theorem uh, with Robert Birkeland, Jeremy Hahn, and Tomer Schlank is that there exist ring spectra Rn such that if you look at, sorry, let me just add some notation first. So I'm going to use subscript, I'm going to use a subscript on K-theory to mean that, like, for example, Tn or Kn, to mean that I first take K-theory and then I Tn or Kn localize. So maybe I'll write it like this. Okay. And so, okay, so the theorem is that there exists ring spectra Rn such that the Tn local, Tn plus 1 local algebraic K-theory of Rn is isomorphic, is not isomorphic to the Kn plus 1 local algebraic K-theory of Rn. Okay? And so this proves a telescope conjecture at height n plus 1. So here n is at least 1. Yeah, because clearly these localizations have to be different if they're producing different outputs. So maybe I'll make some remarks. So Rn is really specific. So you can take it to be the following thing. You start with a ring spectrum called VPN. I can roughly tell you what VPN is. It's a spectrum whose homotopy ring is just a polynomial ring over the p-local integers on V1 all the way up to Vn. So it sort of detects information about the first n v's, but then nothing really after that. So it's a height up to n object. And there is an action of the integers on this, which is some kind of Adams operation. And you can take the fixed points of this action. And so maybe I will give you some, to be more concrete, when n equals 1, you can take the following thing to be true. So you can take L, which is the connective cover. It's the connective cover of the Adams summand of Ku, of topological K theory localized at a prime P. So the Adams summand of that is it's sort of the indecomposable summand containing the unit. And that has an action of Adams operations. You can take the fixed point of any non-trivial Adams operation on that. And that will work. Okay, and if you choose your Adams operation correctly, you could actually take R1 to be even the following thing, which is the -1 connective cover of the K1 local sphere. If you choose sort of a generating Adams operation. Okay, so there are certain ring spectra and they detect the failure of the telescope conjecture. But you'll notice something a little bit funny, which is that the ring spectra that you're inputting, they only go up to Vn, so they're only up to height n, but I'm doing a Tn+1 localization. And yeah, so the reason for that, so the reason you use Tn+1 localization, even though uh, the ring that you're inputting is height n, it's because of Osoni and Rognus's philosophy of redshift, um, which says, I mean, very roughly, it says that K-theory can do this kind of thing where it produces, it sort of shifts the height up by one, and it can produce interesting objects one height higher. Okay, so that's the main result um, but I want to tell you a little bit about how this works and how like why the sort of one of the key things to understand in this story is some computations related to topological cyclic homology. Okay, so how does it work? So the in fact, the theorem is a bit more precise. It gives a particular mechanism by which the Tn+1 and Kn+1 localizations don't agree, namely the following. So you can start with the Tn local sphere, and there exists certain Galois extensions of the Tn local sphere called chromatic cyclotomic extensions. This is just some notation for them. And you should think about the case when n equals 0. When n equals 0, the Tn local sphere is essentially, it's the rational numbers, and this is the extension that's adjoining a primitive p to the kth root of unity. And so analogously to these extensions, in general, there's a z mod p to the k cross action, and they're Galois extensions. So for example, what it means to be Galois extension is that if you want to look at the category, you have Galois descent, which means that the category of Tn local spectra is equivalent to the category of equivariant modules over this ring. And so you have descent. Okay, but even though you have descent for each of these finite extensions, what's sort of not clear from the construction is that you have descent for the infinite extension that you'd get by taking the colimit of all of these. So namely, you can take the Tn local sphere and you can take the colimit over K of all of these extensions. And then, so each of these had a Z mod P to the K cross action, and so this thing has a ZP cross action, and you can take the fixed points by that ZP cross action. And this is something you can give a name to. I'll call it the cyclotomic completion of the Tn local sphere. And this is an idempotent algebra in the Tn local category. So what does that mean? An idempotent algebra it's an algebra such that A tensor A is isomorphic to A via the unit map. And another example of such an idempotent algebra is the Kn local sphere. So this is an idempotent algebra too. And so anytime you have an idempotent algebra, you get a localization of the Tn local category, which is a colimit preserving, it's a localization with a colimit preserving right adjoint. So namely, we have the Tn local category, And taking modules over the cyclotomic completion gives you a subcategory, which is the cyclotomically complete uh, objects. And then because the K local sphere is essentially the terminal non-zero idempotent algebra in the T local category, as a further subcategory, there's the K local sphere. And, oh, sorry, I shouldn't write the sick. And so then you have localizations, which are given by cyclotomic completion, which is just tensoring with the idempotent algebra or K localization. And so the more precise thing that you show is that, in fact, these localizations are already different. Um, that's the more precise thing that this theorem is proving. And so let me explain how that works. So the point is that these cyclotomic extensions, they behave very nicely with respect to K theory, which, yeah. So namely, if you look at K theory, maybe Tn plus 1 localized of some ring, some Tn local ring, and you adjoin p to the k roots of primitive, these higher roots of unity to it. So you tensor, in other words, you tensor with this algebra. Then Ben Maché, Carmeli, Schlank, and Janowski. Oh, so I should have said these Galois extensions, they were constructed by Carmeli, Schlank, and Janowski. And maybe I'll also mention that the theory of Galois extensions in this setting is really due to Rognus. So, okay, so this, right, so Ben Maché, Carmeli, Schlank, and Janowski, they show that the K theory is really compatible with these cyclotomic extensions, meaning that if you take K theory of a cyclotomic extension, you get the cyclotomic extension of a K theory. So namely, you get this. But now the height has shifted by 1. So this is called cyclotomic redshift. And so what you can do with this is it tells you that there's actually a pretty concrete formula for understanding the cyclotomic completion of a K theory, of a Tn local K theory spectrum. Namely, what you can do is you can just take the co-limit as K goes to infinity. So then I'm going to put infinity here instead of a K. And then you can take the fixed points of everything by a ZP cross action that you have. So I'm going to take the fixed points here by, I'm going to take the fixed points here by ZP cross. And I'm going to take the fixed points here by ZP cross. But if you think about taking the fixed points here as ZP cross, that's exactly the formula for the cyclotomic completion. And so what you learn is that this is the cyclotomic completion of the K theory. It's given by adjoining these roots of unity to the ring and then taking the fixed points on the outside. Okay, so the cyclotomic redshift is it's essentially a formula for computing cyclotomic completions of algebraic K theory spectra, of Tn localized algebraic K theory spectra. And this is if R is Tn local. Okay. So, okay, so now I want to explain the rest of how this works, I need to first tell you why this Tn local algebraic K theory is nicely behaved. And why it's something that you can really access pretty well. So one of the reasons for this is this vanishing impurity theorem, which is a theorem of Clausen, Matthew, Naumann, Noel, and Lan, Matthew, Meyer, Tama. And what it says is that for n greater than or equal to 1, Tn local K theory uh, applied to some map, F, let's say, is an isomorphism if, so if you have F, let's say some map of ring spectra, um, has that the Tn localization of F is an equivalence, and also the Tn minus one localization of F is an equivalence. So it's sort of just, it's saying that the Tn localization of K theory just depends on the Tn localization of your ring and the Tn minus one localization of your ring. Okay. And so maybe just to give some examples of what that means. So what that would tell you is that, for example, if you're just interested in the Tn local K theory of your ring, for maybe n at least, let's make n at least 2, then that's the same as the Tn local K theory of just the connective cover of that ring, because the map from the connective cover to R satisfies this property. And another thing it would tell you is that, for example, if uh, if Tn localization of R is 0, then this is actually the same as the Tn local K theory of the Tn minus 1 localization of R. So what this is saying is that you're allowed to use rings that are unlocalized and compute the localized K theory, and you get the same answer as if you had localized the ring. Okay, so this is one nice property of this Tn local K theory. And another nice property is trace methods that sort of let you turn K theory questions into TC questions. So I'll say more about TC later, but or maybe in the next lecture. But for now, TC is just some other functor like K theory, in the sense that it's some functor that takes in algebras and spectra and outputs a spectrum. Okay. And there's a natural transformation called the cyclotomic trace from K into TC. And the theorem that's relevant here is the following theorem, that if you have some map, let's say R to S, which is a minus one, a one connective. This is maybe not the strongest version of it, but if you have a one connective map of connective ring spectra, then you get a pullback square as follows. You can take K theory and take TC, and you get a pullback square using the cyclotomic trace. And yeah, so this is due to Dundas, Goodwillie, and McCarthy. And in fact, I sort of observed that this also, you can extend this further. For example, it also works for minus one connective ring spectra. They don't have to be connective, and that's going to be important. And so okay, so combining, let's combine these this vanishing impurity result with this trace methods result. So what this tells you is that if n is at least 1, let's say, and you're interested, and let's say you have some ring which is minus 1 connective, and its Tn plus 1 localization is 0. So for example, you can imagine R to be this BPN fixed points by this Z, or just BPN itself, some ring like that. then what you learn is that if you're interested in the Tn plus one local algebraic K-theory, then, or maybe you're interested in the Tn plus one local algebraic K-theory of Tn localization of R, then that's actually just the same as the Tn plus one local Tc of R. And the reason is because you can apply this purity theorem to see that the K-theory doesn't change if you replace the Tn localization of R with R. And then you can use this trace methods to see that the difference between K-theory and Tc can be seen as the difference between something where it vanished after Tn plus one localization using this purity theorem again. So the point is just that when you're at high enough heights, Tc and K-theory are basically the same, and the localization on the ring doesn't really matter as on the K-theory side. Okay, and so let me explain now how, okay, so how does that reduce the question to a question about TC? Well, so what were we trying to prove? So we wanted to know that the Tn plus one local algebraic K-theory of something like BPN, maybe I'll put in the Tn localization of BPN, we wanted to know that this is not the same as its Kn localization, or its cyclotomic completion, in fact. But the point is that you can use cyclotomic redshift to, in fact, identify what the cyclotomic completion map is. So the cyclotomic redshift, it shows that this cyclotomic completion, it shows that the map I'm about to write down is just the cyclotomic completion. So it's the map from Tn plus one local algebraic K-theory of this to Tn plus one local algebraic K-theory of first, you just take Tn plus one Tn localization of BPN, and then you take the fixed points on the outside. And this is essentially, it's not exactly true. It's not literally true, but that the map from this ring to this ring is a cyclotomic extension, but it's very close to cyclotomic extension. For example, it becomes a cyclotomic extension after a faithfully flat map. And so this is close enough to cyclotomic extension that that cyclotomic redshift tells you that this is just cyclotomic completion map. So it's enough to show that this is not an isomorphism. So we want to show that this is not an isomorphism. And here's sort of the key fact. Well, okay, sorry. Yeah, so now the point is that the purity in trace theorems, so the purity plus the trace methods, they exactly give us a formula for understanding these algebraic K-theory spectra. Namely, it tells us that this is the same thing as just the Tn plus one local Tc of this BPN ring, fixed points by Z, and that this is exactly the Tn plus one local Tc of sorry, the same ring, so namely BPN, but then you take the fixed points on the outside. And so what you're trying to show is that this is some kind of co-assembly map for TC, namely it's measuring whether or not TC commuted with this limit of taking this Z fixed points. And you want to know, you want to show this is not an isomorphism. And so that's what these theorems buy you. They tell you that it's really just this question of, is this co-assembly map for TC an isomorphism? Okay, so now I want to So this is the bulk of things that I'm going to not explain in the in this lecture series. I mean, there are many more things I'm not going to explain in this lecture series, but uh, the rest of the things that go into the disproof, I want to I hopefully get to say something about in this lecture series. So how do you actually show that this map is not an isomorphism? Well, it's enough to show the following. So you can take this TC of BPN, fixed points by Z, and you can tensor it with a type n with a telescope of height n plus one. Right? And that maps to the same, you can look at the co-assembly map for that. So you can put the fixed points on the outside. And it's enough to show that this is at the level of homotopy groups, this map is not an isomorphism. Because a Tn plus one local equivalence is detected at the level of tensoring with a type n plus one telescope. So it's just enough to check that this map of homotopy groups is not an equivalence. And remember this Z action is coming from some kind of Adams operation on this BPN ring. And the sort of key fact that makes this much easier computationally is that you can actually if you choose your Adams operation correctly, you're allowed to replace this Adams operation with the trivial action. So namely, for appropriate choice of Adams operation, for good choice of Z action on BPN, then you get the following square of isomorphisms. So this is the map that we're interested in showing is not an isomorphism. And in fact, it's just enough to show that the following map is not an isomorphism, where I replace the fixed points by this Adams operation with the fixed points by a trivial action, which I'm going to write as BZ because it's just the cochains on the circle with coefficients in BPN. And then you tensor with Vn plus 1 and Vn plus 1. Okay. So in fact, what this tells you is that it's enough to show that this map is not an isomorphism. So enough to show not an isomorphism. Okay, and really this commutative square is one of the it's one of the most subtle points in the proof. And it uses this fact, maybe I'll call it star one. It uses what's called the Lichtenbaum-Quillen property. Which is sort of, it's a key finiteness property of BPN that I'm going to talk a lot about in the future lectures. So, okay, so that's one of the key facts. But now, okay, so now you're, sorry, I wrote the wrong thing here. Here I should have written BZ. So again, this is even on this side, it's the trivial action now. Okay. Okay, so we've replaced this map, this co-assembly map for this non-trivial action with the co-assembly map for the trivial action. And then the point is that once you're at the case of the trivial action, it's a lot easier to show that it's not an isomorphism because of just some facts that are true more generally. So, for example, so here's sort of the other fact that you can use now. So if you look at the fiber of TC of R, and for some general ring R, just choose your favorite ring R, and you look at this fiber of this co-assembly map. So what we're trying to show is we're trying to show that this fiber is it's Tn locally non-zero. That's what we're trying to show for some specific R, namely BPN. So we want to show that something like this is non-zero Tn plus 1 locally. And the point is that you can, okay, if something is non-zero, then you shouldn't be able, sorry, if something was zero, you shouldn't be able to produce anything that's non-zero using it. And the key point is that this fiber contains, um, it can be used to build TC of R infinitely many steps. Um, so in other words, TC of R is in the thick subcategory of this fiber in a natural way. And so what that tells you is that if you want to show that the fiber is non-zero, it's enough to show that TC of R itself is, if you want to show that this is non-zero Tn plus 1 locally, it's enough to show that this itself is non-zero Tn plus 1 locally, because it's in the thick subcategory of that. And so, right. So maybe this is another fact that maybe I will discuss in future lectures. And then, so, right, so it's enough to show, so you learn that it's enough to show that TC of BPN tensored with, is Tn plus 1 locally non-zero. In other words, that this is non-zero. And this is, it's true by redshift, which indicates n equals 1 and maybe primes at least 5 is due to Ausonian Rogness, and in general is due to Hahn and Wilson. And I want to explain something about this too in my lecture series. Yeah, so let's see, I don't have a lot more to say for today. Maybe what I'll say is that for the future lectures, it will be very helpful to have some basic familiarity with THH and cyclotomic spectra. So I'm going to give definitions of everything, but I'm gonna sort of skirt over some maybe basic properties and facts and go. It'll be quite fast if you're not that familiar with these things. So yeah, it'll be very helpful to have some basic familiarity with these things and some references. Well, there's Nicolaus and Schulze's work on topological cyclic homology and THH. And then there's some nice lecture series and notes by Achim Krause and Thomas Nicolaus that I would recommend if you want to get some familiarity with these things. But yeah, so the plan in the next few lectures is to try to explain some of these key facts that are used in this proof of telescope conjecture, and it will work with THH and cyclotomic spectra quite heavily. Yeah, okay, so that's all I have to say for today.